When last we left, I was talking about diagnosing our model, and I'd given you the first 3 steps in a 7-step model to diagnosing our model. Number 1, is we ask ourselves if our coefficients on our variables or our slopes make sense. Number 2, I want you to look at your standard error of regression, especially as it relates to your dependent variable. So if the average of your dependent variable is 100 and your standard error is 150, you probably don't have a very good model. Third, and only after doing these 2 things, we look at what is your adjusted R squared. We talked about R squared and adjusted R squared. We talked about why we tend to prefer using adjusted R squared. I'm going to go over those 3 things briefly here at the end of slide 14, or at the end of chapter 14, where it talks about all of these as goodness of fit measures, which means how well does my model fit my data? How well does the model fit the data and what it shows in the real world? So, do not scribble equations. Don't do it. I know they're nice, I know they're impressive, they'll look neat to whoever sees your notebook. Don't waste your time. We're talking about the mean squared error to compute the standard error of the regression. We showed this in Excel and in Gretel what the standard error is. In order to compute it, we first have to compute the error sum of squares. We take each actual, subtract its predicted, square it, sum them all up, divide the SSE by the appropriate degrees of freedom, gives you the mean squared error. So first we compute the error sum of squares, then the mean squared error. Then we get the standard error by taking the square root of the mean squared error. Here. Anybody want to learn to do it by hand? Any reason to do it by hand in our modern world? Not really. Have you seen the people on Facebook complaining about their kids' math homework? I didn't do math like this. It's because they don't understand it. It's because they don't know how to do their kids' math, and it makes them angry that they can't help their kid with their math, and it gives you some cognitive dissonance. It makes you angry.
That's changed the way it's taught. It's all new Common Core standards.
Yeah. Oh, it's not Common Core. It has nothing to do with Common Core. Now you're doing Facebook math only. That's wrong. It's not Common Core. It's like, that's just rumor and like, oh, that Obama changed math. No, the dumb, all right?
I work in schools.
Yeah. I mean, Common Core fits it, but we didn't do this because of Common Core. We did Common Core because of this.
Well, it dictates the way that some things have to be taught.
Oh, yeah, that's the point. But we did it because teaching math was wrong.
Right, I mean, like long division.
Yeah.
How they do long
There's no point in doing long division anymore.
They don't do it like that.
We don't do it. We're not going to do long division. We don't do multiplication the same way. We don't teach these things the same way because there's absolutely no point in learning to do, okay, put this and do your long division and carry this down and put a 0 and carry this down. Folks, you're carrying a device that we never thought of when we were doing that. Learning to do long division this way, out 16 different ways to 5 different decimal points, is a waste.
Because it's important to know how.
We want to know how it's done.
It's important for the child to understand how.
So what we're teaching is number theory. They're teaching number theory. If you were ever taught how to do sort of mental math, if you were ever taught to sort of multiply large numbers in your head or do division in your head or square root numbers, if you learned how to do this mental math in your head, you learned number theory and place value theory in order to do these tricks to sort of like multiply 2- and 3-digit numbers in your head. That's what they're teaching now on how to do it. They're teaching the number theory and place value theory. And it's a far superior way. When I see these idiots on Facebook, like, oh, they're teaching my kid wrong math. Well, what are you, Captain Statistician? All of a sudden, you can't balance your checkbook. Now, all of a sudden, you're an expert in mathematics and the foundation of number theory? You're gotta be out of your mind. You misspelled 4 words in that post. All of a sudden, you're an expert? Well, I didn't know. Dropped out of Barber College. All right, they know what they're doing. There's a reason we're teaching this. Anybody ever used a slide rule? Anybody? A slide rule is an old device that you would use to do calculations, where it's like a ruler, except parts of it move. You literally slide it in different directions. There's a little plastic piece that you slide along, and you line up this number and this number and that one, and you read the one off the bottom, and that gives you your answer. It's an old device that most of you have probably never held in your hands. It was antiquated when I was in grade school. And the only reason that some of us in the room might have used them is sort of nostalgia or really cheap schools. That's how you would learn to use. There's no reason to go back to that. And there's no reason to go back to old math. And there's no reason to teach you the long calculation of this. I need you to know that there's a way behind it, and I need you to know what the standard error of the estimate is. All right, I need you to know the definition of it and how we relate it to our dependent variable and what it means. We're going to let Excel calculate this for us. I'm not going to send you through the worthless exercise of doing this equation. Silly, 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 silly. A waste of your time and mine as well. Standard error in Excel, standard error of the estimate. So if we're comparing Model 1 to Model 2, Model 1 is better because the standard error is lower. Ta-da! It's just that easy. Coefficient of determination. 3 was the number. 3 emails and text messages I got asking how to do the coefficient of determination. It's about what I expect. I expect 2 to 4. We're right about hitting the average there. What's coefficient of determination mean?
R squared.
It's just the R squared, yeah. It's an antiquated old-ass term for the R squared that the book refuses to quit using. Yeah. Coefficient of determination, commonly, go ahead and scratch that out and write always, referred to as the R squared, is another goodness of fit measure that is easier to interpret than the standard error. Our book and our slides are following its typical path of teaching you the crap thing with the really bad computations and then teaching you the way it's really done. In particular, R squared, here's your definition that I gave you Wednesday. Quantifies the amount of variation in the response variable that is explained by changes in the explanatory variables. Except we're using dependent and independent, right? R squared quantifies the percentage fraction of variation in your dependent variable explained by your independent variable. That's the definition of R squared. How to calculate R squared? I promised I would present this, and thus here it is. R squared is calculated by 1 minus your sum of squared errors over your SST. It's calculated using your observed and expected. Total sum of squares and error sum of squares, or SST and SSE. Again, do we want to calculate it by hand? No. Here's how it looks in Excel. Thankfully, we go on to adjusted R squared. More explanatory variables, more independent variables, always result in a higher R squared by this algebra. If we use this algebra, more variables will always raise our R squared, algebraically. Therefore, that is not the most important value. The adjusted R squared balances that against the desire to include only important variables. So it penalizes you for just throwing more stuff at the wall and seeing what sticks. The R squared calculates that using only important variables. So here we have an adjusted R squared. It's our 1 minus the actual r squared times a computation of our variables and our degrees of freedom. Now finally, our beloved book gets on board with us. We typically allow the computer to compute adjusted r squared as with the other variables. Finally, we're on board. I agree completely. Compare one model, model 1, with the next model, model 2. Even though the r squared is a bit higher over here, adjusted r squared is what we really look at. So that's why we look at all three of these things. Do our slopes make sense? What's the standard error of the regression? Where do these go? And what is the adjusted r squared? Three of our goodness of fit models we're going to use in diagnostics. Questions about any of these three? Gosh, you guys are quiet. It's creeping me out a little bit. Either that or you're just an exceptional class and I'm going too slow and a bit plodding. Let's go to chapter 15. This is the point in the semester where I sort of start to go a little nutty. This is the point where I begin to leave the book and its order of teaching and its slides behind, and I just sort of go off on my own. I don't particularly like chapter 15 and how it goes through and how it presents some of this. I think it's unnecessarily dry. I think it skips what is important and focuses on what is unimportant. I think it does a lot of tests that you very rarely do in the real world and focuses on them too much. So I'm going to hit, really what I'm going to hit and ignore everything else. Things we look at in chapter 15 is tests of individual significance. So if we look at our variables and we have y is a function of an intercept plus beta 1 x1, beta 2 x2, and some unknown error, we have three variables here, right? Variable 1, variable 2, variable 3. Conduct tests of individual significance. So we have to ask ourselves, do these three variables matter? Does this matter? Does it give us any predictive ability in our model? Does this one matter? Does this one matter? Individually, we have to test each of our variables and see, does this actually matter? Are individual variables significant? That is step 4 in our model diagnostic methodology. Are individual variables significant? We conduct tests of individual significance. Chapter 15.1. We test to see if our individual variables are significant. That's what we'll be covering today, among other things, hopefully. The second part is conduct a test of joint significance. So what this says is we have to see if this is significant and this and this. A test of joint significance says the next thing we need to do is, what about these two together? Are those important? And what about these two together? Are those important? And what about these two together? Are those important? What if we have a variable with what if we have a model with 6 variables in it? This gets big fast, doesn't it? Here's a trick. If your individual variables are significant, they're probably going to be jointly significant. You do this, but you don't do it a whole lot. And that's why I'm not going to focus on joint significance. So I'm largely going to skip 15.2. It's a lot of trouble, interpreting it as different, and we simply have time constraints. We're going to talk about linear restrictions. We're going to talk about interval estimates a little bit. And we're going to talk about the assumptions of the ordinary least squares estimators, which we've already done to a degree. For instance, an assumption of this model is that your data needs to be linear. We've talked about that, right? And that we need linear relationships. So I've built some of this in already. I just hate this example. Analyzing the winning percentage in baseball. Okay, so we're looking at a winning percentage and we're trying to determine what might have an effect on the number of wins. Is it things like batting average or a low earned run average or both? All right, very well. So what we do is we look at tests of significance. So our first model is predicting our winning percentage with just batting average. Our second model is predicting winning percentage with just ERA, and our third model is predicting winning percentage with both. Everybody see that? Okay, so we have our statistics here. Which one has the lowest standard error? Model 3. Lowest standard error, Model 3. So that, okay, lends some credence to it. Which one has the lowest adjusted R squared? Or the highest adjusted R squared? Model 3. So it's looking like Model 3 is positive. Looks like both of these variables might have something based on what we've already looked at. Let's look a little deeper. We can test these variables for individual significance. Thinking about the coefficients on these variables, what would be a way to tell which one may be more important or less important? Thinking about the coefficients that Gretel or Excel spits out, what might be some ways to see what's more or less important? Their size. What do we mean by size? What did I hear back here?
Larger coefficient.
A larger coefficient. What if, mathematically, one of these works out to be 0? That means that anything times a 0 is a 0, right? So that means that our variable 1 is effectively going to drop out of this model. It tells us it's not going to be that valid. Variable 1 doesn't matter if its coefficient is 0, or even if it's really close to 0. So what we mostly have to do is we want to run a statistical test to tell us are our coefficients equal to 0? Well, how do we do that? Fortunate for us, this is a statistics class, and we can follow the statistical pattern I gave you at the beginning of class, the beginning of the course. And number 1, we can define a null hypothesis. Like, our null hypothesis can be that the coefficient on this variable is actually 0. I know Excel spit it out as 2, but 2 is pretty close to 0. how do we know that that 2 is statistically different, statistically significant from 0? We have to run a statistics test. So our alternative hypothesis is that it is not equal to 0. So then we run a statistical test. Anybody know what test we run? Test for differing means. Follows a t-distribution. It's a t-test. We run a t-test. So we test to see. By far the most common hypothesis is to test if an individual coefficient, if it differs from 0. If a coefficient is equal to 0, it implies the explanatory variable is not significant. Yeah, just what I covered. Computer-generated output. Computer does this for you. So when it is done, the computer is going to give you a t-stat, a test statistic, and a p-value. Define the null hypothesis, run our test, get a p-value. Step 3, interpret that p-value. How do we interpret the p-value? Again, if the p is low, the null must go. Do we want our variables to equal 0? No, that would mean they're insignificant, right? Do we want insignificant, unimportant variables? No. Powerful, strong, predictive variables. Variables that are very related to our outcome. So we don't want this. So what's better, a high p-value or a low p-value? Here is the confusion I saw on the test. Here is the confusion I saw on the test, interpreting your p-values. So I wanted to specifically go over this here again. We have set up a null hypothesis and an alternative. Our null hypothesis is that our coefficient is 0, meaning that our variable is useless, that it has no explanatory power, that it has no impact on our y. We don't particularly want that to happen. We want to find, typically, that our variables do have an effect. So we run our test and we get our p-value and we interpret this, and if our p is low, this must go. If our p is low, we say that it's not equal to 0, therefore it must be something other than 0, therefore it must have predictive power. So in this case, low p-values are better. Low p-values are better. If the p is low, the null must go. The null is that our coefficient is equal to 0 and that our variable has no power. So when we run an output in Excel, we get something that looks something like this. We've talked about the coefficient. We've talked about the standard error. Now we're going to talk about the t-statistic and the p-value. The p-value on batting average is what? 0. Or 0 out to 5 decimal places that this gives us. Is that low or high? 0 is pretty damn low. P-value on ERA, also effectively 0. So what do we conclude about these two variables? They are good or they are not good? Again, here's the confusion I saw in the test. If the p is low, we reject this null hypothesis. We reject that this number is equal to 0. We reject that this 3.27 is really statistically close to 0. We say it's not statistically close to 0, therefore this number must matter a lot. Even here, this number is very small, negative 0.11, which is a very close number to 0. But ERAs are a lot smaller than batting averages. They're small numbers. So you can't say, oh, 1.1 is too small. You have to do a statistical t-test based on sample sizes and all sorts of other things. And here we get a p-value that's effectively 0. Again, the p is low. The null hypothesis that that number is 0 must go. And we assume that the number is sufficiently different from 0 based on that. And we assume that that is a good variable. Another way to do that is many statistical softwares build a confidence interval for you. A confidence interval is plus or minus such and such. So if I were to go around and measure the height of all the men in this room, our average would be about 5'10". So can I say the average height of men at IUS is roughly 5'10"? Not really. I only have a sample of about 16 of us. And 16 is a small sample to estimate the average height of 1,500 men on campus, whatever it is. It's a big reach to estimate 1,500 based on 16. So what I would do is I would build a confidence interval around this. I would say I'm 95% confident that the average height of men on IUS's campus falls between 5'7" and 6'1". I'm 95% certain it's in here somewhere. I'm willing to accept 5% of error. I'm willing to accept a 1 in 20 chance that I'm wrong. But I'm 95% certain the real average is going to fall somewhere close to this within this range. The software does similar things. For batting average, it calculates the coefficient, but it says, I could be wrong. So I'm going to build an interval around that. I'm going to build an interval that says, I believe the real coefficient, the real value of this variable is 3.27. But it could be as low as 1.9 up to 4.65. It could be somewhere in here if we have to be 95% accurate. Does this range include our dreaded 0? So we can say, for instance, we're 95% certain that this variable isn't effectively 0. We're 95% certain that this is a good explanatory variable that belongs in our model. We have faith in it. We believe in our little variable. The little variable that could. Because we know that this range does not include 0. Again, down here, we know that the coefficient on the ERA is negative 0.1, but it could be as high as 0.08. It could be as low as 0.15. Does this include 0? No. So we're fairly certain that this might be a good variable. So step 4 is we look at each of our variables to determine if they are significant. We look at our output, we analyze our p-values to determine if each of our variables are significant. Questions?
What are we comparing the p-value to? Anything?
An excellent question that I'm glad someone asked. How low is low enough?
Our alpha?
Yeah, it's your alpha. You're comparing to your alpha. Perfect. Flawless. But now that makes the question, of course, what should alpha be? Yeah. Yeah. I mean, you get to set your alpha. You get to decide whether or not these variables are effective. Sort of the academic standard for publishing your results, for putting things in paper, sort of the universal, speed limit of p-values is We say that your variable is significant at the 10% level. So this is sort of your drop dead mark above and below. Above this and your variable is probably bad. Below this and your variable is probably good. Yeah.
Like on the homework last night, or when we did
Yeah.
regression, Excel was already set up for 95%.
Yeah.
So I just ran that.
And that's perfectly okay. Excel is sometimes set up to do a 95%, which would be a 0.05 confidence interval level. If we want to be very, very certain, if we're testing whether or not we may have found a new cancer drug, we might use as our p-value, as our cutoff. But this decision is roughly up to you. Eventually, closer to the end of the semester, we'll talk about how researchers might be twisting their models to just barely get their numbers on this good side of 0.10. They actually call it p-hacking. Actually, a paper is written about how researchers are p-hacking their variables. I love that term. It's just one of my favorites. Recently, they went back and retested something like 900 psychology papers and couldn't replicate their results and couldn't get low p-values. We'll talk about that too. So this is step 4 in our model diagnostic model. Are our individual variables significant? This is important. This is important. Stop here and write this down or whatever you're going to do. Because I will get assignments from you otherwise where you'll run your model and you'll say, okay, I'm trying to test this and that. And I'm using these 5 variables, 1, 2, 3, 4, 5. Okay, so I use them and this is my standard error and this is my R squared and my slopes make sense and my adjusted R squared is 0.8, so I think that's good. And these 2 variables don't make sense. Or these 2 variables aren't significant. Thank you very much. That's not where you end your paper. Alright? You don't stop there. If you have 5 variables that you're running and you find that these 2 are not significant, you should eliminate them. You should dump them out of your model and rerun with these 3. Because this will now be a much better, more predictive model. So you dump these 3, you dump those 2 insignificant variables and you rerun. Now that you've rerun, you go through your steps again. Do my slopes still make sense? How is my standard error? How is my R squared? Do my variables still make sense? Are they all still significant? I have seen cases where you start with 4 or 5 variables and you say, oh, this one's no good, eliminate it. Now another one's no good. You have to eliminate that one. You continue this until you get a good model that you believe in. You may have to do these 10, 15, 20 times to get a good one. Don't put the first 14 in your paper. Put the last one in your paper. You might start by saying, I started with these 6 variables. I found that these 2 were no good. So here's my model with these 3. Thank you. All right. That's a model we can believe in. So you need to find out if your individual variables are significant, and if they're not, their history. Questions on this? Questions on interpreting your p-value? We never interpret the p-value on the intercept. We don't care. The intercept is just the intercept, so we never interpret the p-value on the intercept. Yeah?
I don't know if it's a question.
Probably not.
Okay, like ERA, a low ERA is good. Like,
Yeah.
Okay, of course, with a higher value, so would that affect coefficient, like how one's more productive for the team? Like if you were looking at golfers and you're, so you don't want to see who had the highest swing.
yet it has the lowest.
Right, so when ER is the same, I didn't know if that would affect it.
What you're really looking at there is this, remember the sign on these? Because the sign tells us that lower is better. So that's what we're looking at in step one is, do our signs and slopes even make sense?
But because it's negative and you know that ERA is okay, then it makes sense.
Right, that makes sense to us because a lower ERA is better. Also, we look at our standard error at ERA and we see that it's very small. So what that tells us is that small changes here might make a big difference. Which is true because ERA goes from, 0 to like 4 or 5. And beyond that, you're not really in the pros anymore. Like that's pretty much where you max out. So there's not a lot of range in there. There's not a lot of variation. As opposed to batting average, which might go from, and then it looks like they're using it in hundreds here. Batting average might go from 100 for a pitcher up to 380 for someone who's having a record year. A record year in baseball that they then collapse near the end of the season in a historic fashion, melt down in an amazing way, and we call that team the Washington Nationals.
They call their manager unemployed.
And they call their manager unemployed. That guy is in baseball what we refer to as a goat. That guy is gone. Not greatest of all time either. He is. He'll never get a management job again. That was just an epic meltdown. Just epic. In every way. It's a great time to be a baseball fan. Except that I'm a Reds fan. And the hated St. Louis Cardinals have home season throughout the playoffs. My boss at work is a season ticket holder for the Kansas City Royals. She just moved here this year, and she still has season tickets. So she's already paid for all of her playoff games. Like wherever, however deep they go, she's paid. She has tickets. She's going.
She had those a very long time?
She's had them in decades.
That's what I was saying, 'cause decades ago they weren't for anything, and
Yeah.
now they're pretty.
They haven't been good since I was in diapers. They haven't been good for decades.
Bo Jackson.
Yes, Bo Jackson and George Brett were there. But yeah, she's absolutely thrilled. So the one thing my boss and I have in common as baseball fans is our utter and deep hatred of the St. Louis Cardinals. As all right-thinking people should, right? Here we cover intervals for the parameters, so it talks about the upper 95. I'll let you go through that on your own. I'm going to pull off of the notes. I'm going to pull off of the slides for right there. We're not going anywhere. I've still got 19 minutes, so don't panic. But I want to give you the next step in our model here, which is step 5. Which is we have to ask ourselves if our independent variables are correlated with each other. Are our independent variables correlated with each other? Someone will make this mistake in a paper. Someone will make this mistake in a paper where you're attempting to, let's look at our house example again. Where we're trying to predict real estate values in a certain area, and our x's, our explanatory variables might be square feet again, the number of beds, the number of bathrooms, this is in Florida is what we're looking at, so we'll look at miles to the ocean, so it's distance to the ocean in miles. And because we found another data source we really like, we know how many How many blocks you have to walk to get to the nearest beach? Well, you can begin to see a problem here, right? Because these two things, how far the house is from the ocean and how far the house is from the ocean, are roughly the same thing. If they're not the same thing, they're going to be, if not equal, which is that symbol, they're going to be very nearly equal, which is that symbol. They're going to be very close. They're going to be highly correlated. And this is bad. This is really bad. We call this condition multi-collinearity. We call this condition multi-collinearity. And we don't like it. It's a problem. We test to make sure our variables are not correlated with each other. Because here's what will happen if you have multi-collinearity in your model. Two things typically happen. Number one, one variable will have a negative slope and one variable will have a positive slope. So it will look like one of them is strongly positive and one of them is strongly negative, and both of them will be significant. They will both have low p-values, and they'll look outstanding. Here's the second thing that typically happens when you have multi-collinearity. Your R squared often shoots up to about 0.99. Invariably, someone will run this model, they'll download data for their project, they'll run this model, they will have fallen in love with their R squared. It's the only thing they'll look at. They won't do this because it's a crap ton of work. And they won't diagnose this going through this perfectly reasonable model. They'll skip down here and look at their R squared, see it's 99, I'm good, print it, send it in, we're out. Typically a very bad idea. If you don't test for multi-collinearity, very often your R squared will shoot to 98 or 99%. This is actually a diagnostic tool to see if you have multi-collinearity. It's a diagnostic tool to test for that. So then what you have to do, if you think you have multi-collinearity, is you want to do the equals correlation function in Excel to test for all your variables. But we've got 5 variables over here. So we want to test square feet against number of bedrooms, and we get a collinearity there. Whoops. I have nothing. That was an error on my part, wasn't it? So we want to test square footage, and we get a collinearity there. Then we want to test it against bath and get a collinearity there. Miles. Blocks and get a collinearity there. But then we need to test all of these against each other. Beds against square feet. What's the correlation between beds and beds?
1.
Beds and bath, bed in here. So we have to do it for all of them. So we build this sort of correlation matrix. We build the square of a correlation matrix. Conveniently, in Excel or in Gretel, there's a command where you just highlight your variables and click correlation matrix. You click on tests and then click correlation matrix, and it spits one of these out for you. And you can just print it off and look for numbers that are highly correlated. Excel has no such function because Excel is not built to do modeling and Gretel is. Excel is not built to do this natively. Can you do it? Sure. You can put your little variables and put your correlation functions in there and do it by hand, no problem. It's just a little more time consuming. You get the same answers, you can do it. If you love Excel, it's okay to love Excel. You're going to need it throughout your career. You know when the next time you're going to see Gretel is? Probably never. But know that Gretel's faster at doing it. SAS has one built in, R has one built in. Every statistical package has a correlation matrix built in. Why? So we can test for multi-collinearity. Now, what's the obvious question to ask now?
How do you test for it?
Yeah, how high is too high, right? How high the correlation is too high. Again, it's sort of like, you'll know it when you see it. If you see a problem, you'll know it's too high. As a general rule, anything above 0.8, anything above a 0.80 correlation is really suspect. Anything above that is really suspect. Questions on any of this? I've taken you from 3 and I've added 2 more steps to testing our models. 2 more steps in our diagnostics to diagnose our models. We have 2 steps yet to go. I'll explain those and demonstrate them on Wednesday. So I'm going to follow our normal pattern of slides and chalkboard and theory here on Monday. Then on Wednesday, I'll toss the last 2 in here. We're going to go through these in Gretel, and I'll give examples of them, and we'll look at some p-values and t-statistics. We'll look at testing individual variables. We'll look at seeing if our data is correlated with each other. And we'll do examples, and then we'll get to test some of these for homework. Questions?